Have you ever wondered why a compass needle moves when brought near a wire carrying electric current? Intriguing, isn't it? Today we dive into the fascinating world of the magnetic effects of electric current. Starting at the very beginning, imagine an electric current running through a wire. Now, what you might not know is that this current is not alone. Around it, invisible to the naked eye, a magnetic field forms. This phenomenon, my friends, is what we call the magnetic effect of electric current. But what is a magnetic field? Picture it as a region around a magnetic material or a moving electric charge within which the force of magnetism acts. You can't see it, but it's there, like the air we breathe. And just like air, it has a direction, from the magnetic North Pole to the magnetic South Pole. So, when an electric current flows through a wire, it acts like a magnet. An intriguing concept indeed. But how does it happen? It's all about the electrons, those tiny particles that form the current. As they move along the wire, they create this magnetic field. The strength of the field depends on the magnitude of the current and the distance from the wire. The greater the current or the closer to the wire, the stronger the magnetic field. How about a practical example? Consider a simple electric bell. It uses the magnetic effect of electric current. When you press the switch, current flows through the coil, creating a magnetic field. This field attracts the iron strip, causing the hammer to strike the bell, and voila, you hear a sound. But now, when we coil the wire, we get what's called a solenoid. A solenoid is a coil of wire that acts like a bar magnet when a current passes through it. Its magnetic field pattern is very similar to that of a bar magnet, with distinct north and south poles. And then there's the electromagnet, a type of magnet where the magnetic field is produced by an electric current. The magnetic field disappears when the current stops. Electromagnets find numerous applications in our daily life, from lifting heavy iron loads in scrapyards to being an essential part of electric motors. In conclusion, it's fascinating to see how electric current and magnetism are intertwined. We started by questioning why a compass needle moves near a live wire and discovered the magnetic effects of electric current. We dived into magnetic fields, learned about their direction and how they form around a current-carrying wire. We saw how this principle applies to everyday objects like the electric bell. We then explored solenoids and their resemblance to bar magnets when carrying a current. Finally, we touched upon electromagnets, their properties, and their wide-ranging applications. This is a great example of how science allows us to understand the invisible forces that shape our world. So, the next time you see a wire, remember there's more to it than meets the eye. It's not just carrying electric current, it's creating a magnetic field, acting like a magnet. Now, isn't that something?